Okay, we're now continuing with descriptive statistics. It's actually something that we've been doing already for quite a while. So descriptive statistics is defined as numerical or graphical summary of data. And graphical summary of data is exactly what we've done already with box plots. But you can also calculate summary statistics. So you can convert a long data table, for example, by calculating means. And oftentimes you report standard deviations in brackets. So those are summary statistics. And you can also then use those summary statistics for other graph types that we'll cover in the next lab. So for example, bar charts typically show your mean by the height of the bar, and then the standard deviation as this error bar. So numerical summaries are generally used to describe the center of a distribution, the spread of the distribution, and the shape of the distribution. And we have already covered a bunch of summary statistics that the software calculated for us in the background when we did the exploratory graphics. So we had medians in the box plots, ranges, quartiles, the interquartile range. So range would be one measure of spread, and the interquartile range would also be a good measure of spread. You can also have other percentiles, so these are all percentiles. And then there's a whole bunch of additional descriptive statistics that we now cover. So we're looking at the mean, which is the synonym to average. There's also a mode. Less commonly used are harmonic mean and geometric mean, but I will quickly explain to you what those are. Weighted means are also not really very often used in statistics, but it does have applications, so this one I will explain. And then of course we have standard deviation, variance. Coefficient of variation is a useful statistics, and there are a number of others that are also not commonly used. And then last but not least, we already talked about skewness and kurtosis. Just as a reminder, if your distributions are not symmetrical, if they are skewed to the left, that would be a positive skewness. If they are skewed to the right, it's a negative skew. And kurtosis is usually defined as 3 for a normal distribution, and anything narrower would be larger 3, and anything wider would be smaller than 3. So let's get into this a little bit more deeply, starting easy with the arithmetic mean. So the mean is defined as the sum of my observations divided by the number of observations. And there are actually different formulas for the population mean and for the sample mean. The formula is actually the same, except you use different symbols. So the population mean would be a parameter, and so that's indicated by this mu, and the sample mean is an x with a bar on top. So sum is simply calculated for a counter from I equals 1 to the number of observations. This is usually left out. And then xi are my numbered observations. So it would be the first observation for I equals 1, the second observation for I equals 2, and so on and so forth. And so you do exactly the same thing for the sample mean. In this case, I have left out the notation here, I equals 1 to n. That's always implied by this sum. And just to give an example, 2 plus 5 plus 8 divided by 3 observations equals 5. So I'm sure you were all familiar with this, but you may not be familiar that there's a difference between the population mean and sample mean. This may not be very convincing here because it's the same formula, but there are differences that come eventually. So median we already covered. This is simply the 50th percentile. One thing to notice, if you have an uneven number of observations, this will be the central observation. And if you have an even number of observations, the software would typically report the average of the two central ones. So 50% of your observations are below, 50% are above your median. Mode is the value with the highest frequency. So that is sometimes used if you have ordinal scale data, so some sort of scoring system or grading system from 1 to 6. It may be useful to ask which one is the most common observation. But if you have a ratio scale variable that often is a real number, then this doesn't make a lot of sense because all your numbers are different. Geometric mean. Geometric mean is not very often used, but it is essentially a mean on a log scale. So in this example here, my values double every tick. So I go from 1/8 to 1/4 to 1/2 to 1 and to 2. If I wanted to calculate the average of 1/4 and 1, it would be 1/2 on this log scale. And so the way this is implemented, instead of averaging everything up and then dividing, you multiply everything and then take the square root. So same idea, but different operators. And this does have its uses. So for example, if you have a situation where you increase your price of some item by 40% and then by 60%, what's the average price increase? So in that case, it's actually not 50%. So if you calculate 100 times 1.4 times 1.6, then you get $224. But if you were to calculate a 50% increase twice, that gives you $225. So there the average does not work, and it's because you multiply those. As soon as you want an average of two numbers that are multiplied, then you need to use a geometric mean. So I can work this out with my formula here. So I multiply all my price increases and then take the square root of the number of price increases, and that gives me 1.4967, so something close to 1.5, but not exactly 1.5. But this one, if I multiply the $100 twice, it would actually work out. So harmonic mean is again something similar, but in this case for ratios. So it's the average of ratios, and this is also very useful. The formula for this is that you take the inverse, so you don't divide by the number of observations, but you divide n by your ratios. So let's illustrate this with an example again. So if I buy $100 worth of shares at $40 per share, and then I buy another $100 worth of shares at $60 per share, what's the average share price that I paid? Or if you drive 10 kilometers down the road at 40 kilometers an hour and then 10 kilometers at 60 kilometers an hour, what's my average speed? So it's all the same kind of question. So in each case, it's actually a ratio that I try to average. And then this formula comes in handy. So I can just calculate my 140 divided by 160. So these are the two ratios that I have. And then I divide inverse by that sum, which gives me 48. So 48 kilometers per hour or $48 per share is my average share price. So it can be handy to, if you have problems like this, to use the harmonic mean. This is otherwise pretty hard to figure out. And then last but not least, we have the weighted mean. That's actually also an important descriptor that you'll likely come across in analysis sooner or later. So this weighs my individual observations by some sort of weighting factor. And a good example is, let's say you want to calculate the average species frequency across a province, and you sample different ecosystems that have different sizes. So in this case, you would have to calculate averages for each ecosystem from the sample data, and then your averages become your new observations here, and each is weighted then by the area. So in order to get the average species frequency that is considering the different areas of the province, you multiply the area by the average of each ecosystem and then divide by the total weight, which is the total area of Alberta in this particular example. Now, moving on to measures of spread. We already covered percentiles, quartiles, and quantiles. Percentile simply means the percentage of observations counted out through your distribution. So for example, the first 23% would be this shaded area here. That would be your 23rd percentile of observation. So you can calculate that for any number that you like. You often use percentiles to exclude extremes. So if you want to get a range statistic that is not quite as sensible to outliers as your true range that goes from the minimum to the maximum value, you can calculate a 5th to 95th percentile. So this would be the range minus the extremes. So 90% of observations would fall between the 5th and the 95th percentile. And these are good descriptors for any kind of data. So normally distributed or non-normally distributed, they are widely used. And just as an aside, the percentile is often abbreviated by a P. So p equals 0.23 means this 23rd percentile. And that's exactly what the p-value in statistic is. So a p-value of 0.05 means a 5th percentile. Now, I already told you before that percentiles are a little bit context dependent. So sometimes you're talking about this end here of the 5th percentile on this side. So it depends on the context. It's really confusing in the beginning, but you kind of get the hang of it when you interpret percentiles in context. So how would it make sense? How is the sentence constructed? If I say, oh my God, I'm in the first percentile of the class scores, that means that 99% are better. But if you say, oh, I'm in the first percentile, yay, that means 99% are lower than you. So that you have to keep in mind. It depends almost on the pronunciation, which side of the distribution you're talking about. Okay, next up are variance and standard deviation. So those are really important measures. They are calculated in a fairly straightforward way. So you have to first calculate the mean, and then you subtract the mean from each of your observations. So this gives you positive and negative values. And in order to get rid of this, you square this. So all the values become positive, and then you divide by the number of observations. Now, in this case, population and sample variances are slightly differently calculated. So you use a different notation again. So your mean here for the sample variance is x bar, and you divide by n minus 1. And if you're wondering why, that's a very good question. So we'll get to this. That's definitely not intuitive why that should be the case. But it really is true that this works out. So the formulas are different, and I've shown you here the formulas for the variances. They're actually notated as a symbol square. So if you take the square root of this, you end up with a standard deviation. So the standard deviation is simply the square root of the variance for both population and sample variance. And that also makes sense because I squared the differences here. So in order to come back to regular units, it makes sense to take the square root of this. So standard deviations is actually the descriptive statistic that you report most of the time. And we can also look at what the standard deviations describe. So if you have a normal distribution with a mean, and you look at the interval of plus minus 1 standard deviations away from the mean, this would represent 68.27% of your data. So typically people say 68%. 2 standard deviations would capture 95% and something of your data. And then the 3 standard deviations are 99.7% roughly. You can also calculate intervals that are exactly 95% or exactly 99%. So in this case, you have odd standard deviation numbers. So plus minus 1.96 standard deviations for a normal distribution would give you 95% of observations would be captured within those intervals. So if you see a bar chart with standard deviations, this is what that means. So plus minus 1 standard deviations means that 68% of your actual observations falls within this interval. Now that's different than standard errors, and we get to standard errors later. So standard errors are actually becoming a little bit more interesting. This actually goes into inferential statistics. That's not the same as standard deviations. So standard deviations simply describe data. Those are descriptive statistics. Standard error is not. And then last but not least, we have another metric that I want to mention. That's a coefficient of variation. This is simply the standard deviations divided by the mean times 100. So it's a standard deviation expressed as percentage of the mean. And this can be useful if you want to describe the variation of different variables. For example, if you want to compare height and dBH and ask which is more variable, that cannot be done with just the standard deviations because they're simply different units. But you can express them as percent, and then you can make such a statement. Or you may want to say, oh, is my height more variable at site 1 or site 2? If those sites are also different environments or different ages, they may have different heights, and that would drive part of your variation. So by expressing this as a percentage you make them comparable. But important to keep in mind, this requires a natural zero value, so your variables have to be ratio scale. This would not make sense for any arbitrary zero values. So if you have interval scale like temperature, don't do that. That would give you complete nonsense. You can try this out for yourself if you want and think that through. Or ordinal scale data is actually also usually not. You have to watch it. So they may also have an arbitrary zero value. So for example, if you set 0 to what looks normal to you, like I recommended earlier in one of the videos, then this statistic would not work.